Good morning, good afternoon from Barcelona, and welcome to a new Rhino webinar. This is Pedro here, and I'll be presenting today a new installment of this series. In today's webinar, Alejandro and Daniel will showcase a web tool for daylight compliance estimation in urban design. This tool was developed using Rhino.Compute and explore the potential of data science and machine learning techniques to enhance its predictive accuracy and efficiency. About our speakers, Alejandro Pacheco is an architect working at White Architecture in Sweden. He's specialized in sustainable urban development and performance analysis. And Daniel González is an experienced web developer who will share insights from integrating Rhino and web applications thanks to Three.js. So yeah, I'll let Alejandro start presenting, and as always, I'll be collecting your questions in the chat for the Q&A session that we will have at the end of the presentation. So Alejandro?
Yes, do you see my screen?
Yep.
Yes.
So good afternoon, everyone, and welcome to our seminar on this innovative tools for daylight compliance using Rhino.Compute. We want to thank McNeel for this opportunity to talk about our experience using Rhino.Compute. We can skip the introduction since Pedro has already introduced us. So this tool that we're going to present today was developed for White Architecture, that is a leading Scandinavian firm known for its dedication to sustainability. And here is the agenda of what we're going to start talking about now. First, we're going to start with the introduction to the tool that we're going to show. Then we're going to talk a little bit about the predictive method for the tool that was developed before developing the tool. Then we're going to discuss our development journey, and we're going to finish with a summary of the key learnings we drew from developing this tool. And finally, the Q&A session. So first, a little bit short summary about what the tool does and what was the goal with developing this tool. So the goal is to empower architects to make informed decisions on daylighting, especially during the early design stages. And it is born from two challenges. First challenge is that our urban environments are continue to grow denser and denser, which makes it harder to generate buildings with good daylighting, especially in places with scarce daylight, like it can be Scandinavian during the winter. And the second challenge that is the reason for this development is that traditionally, assessing daylight requires a very tedious process of model exchanges between architects and daylight experts. So import and output and changing software and adapting the model and so on. And this is quite time consuming and very slow and inefficient. So the idea is that with this tool, we want to try to provide a rapid and automatic daylight performance prediction so that the architects can quickly iterate themselves on their designs, and they can ensure that once they send their models to the daylight experts for actual simulation, there are no big surprises. So this application is based on a predictive equation. This equation was developed together with two researchers on Lund University, that is also located in Sweden. They are Marie-Claude Joua and Jason Burnas. The predictive equation that you see on the screen predicts the median daylight factor in a room, and that's the reference metric that we use to evaluate daylight in Sweden. And the equation was obtained through a research that used the data science techniques. We did like a regression analysis on a database that contained data for about 11,000 rooms, both like simulation results for daylight and like a lot of different parameters on the room, geometrical parameters on the room, the windows, and so on. And finally, we identified the parameters, the geometrical parameters that were more connected with the daylight performance, and we created this equation that was connecting these few parameters. The 4 parameters that we ended up using are the room height, the room depth, the window size, expressed as window-to-wall ratio, and the daylight access on the window expressed as vertical sky component. So the first application that we developed based on that equation, where Danny and I first collaborated on this, was to make a super simple tool that evaluated the daylight in a room. I'm going to show it to you now. So the idea is that this tool can be used by anyone, regardless of their prior knowledge on daylighting. And first, users, this is what the tool looks like. And first, users define a little bit the context, like what's happening outside of the room. Defining, like, for example, the width of the street, of the height of the building in front, and so on, if it's a street. Or if it's a courtyard, the dimensions of that courtyard. And for more complex configurations, the user can calculate himself vertical sky component and just introduce it manually. And then the user sets the internal geometrical parameters of the room, the height, the depth, the window size, or the balcony, if there's a balcony. And then the room, and then the tool is categorizing, here you see on the lower part, it's categorizing in 4 categories the room, from like poor daylighting to mediocre daylighting, acceptable, or good. So we recommend the 2 higher categories, the acceptable or the good, and so that the user can change the different parameters until if it's not enough, the user can change the different parameters until you come to the acceptable level. So that gives like very quick input to the user to see like what they can do, what they need to do to comply in a specific room. So this is the Grasshopper script that is behind this tool. It's a super simple script that is just creating this dummy, like you see here on the right, of a room. That is the one visualized in the website, and then it's also like calculating like the result of the equation based on the input parameter, and that is used to classify the room. I just want to show you what it looks like in Grasshopper. See, this is dummy. You have here the input parameters, like this one's the window size. See, like the window size changes, or room depth and stuff. And then you have the output, all the outputs. So all the outputs include like the geometry of the room. These are some dimension lines, and then this is like the result of the equation that is based to do this classification. So the way that once you upload this Grasshopper script to Rhino.Compute, the way to get inputs and produce outputs to interact with anything outside of Rhino.Compute are these components here, if someone has never used Rhino.Compute. So you get these get components that are used for the input, anything from geometry to integers or strings. And then you have these 2 on top, context bake and context print, are the ones used to produce output and send something from Rhino.Compute somewhere else. So the context bake is used for geometry, anything that is geometrical output, and the print is used for anything that is more like a string or numbers or this type of data. So it's a little bit just to show. And then here is we're gonna show you like the actual tool that we ended up developing. After we did this first tool, we convinced why to invest on a more complex version of the tool that would that could be used to upload a simple model for a whole building, and then have like individual estimations of each of the rooms of the building. And for this, we counted with the assistance of a very competent and very motivated intern that I think is watching today. It's Isaac. So the idea here is that the users could upload a model, like you see here, a Rhino model, into a website, and then it automatically identifies all the layers, and then it tries to identify what geometry is contained in each layer, if it's rooms or if it's windows and so on, and then see like there's like some objects that were not correctly identified. It gives you a warning, and then you just click on run estimation, and it runs the equation for each room, and it gives you results. It categorizes the rooms in these 4 categories that we showed before: poor, mediocre, acceptable, or good. And for those rooms that are in the 2 lower categories, poor and mediocre, if you click on them, it gives you like information about how you can make this room acceptable. It gives you like I see here that the units are wrong. It should be millimeters, but it gives you like, in this specific case that we clicked, it should be like you can decrease the room depth by 1.1 meter, or increase the window height by 0.6 meters, or increase the window area by 0.6 square meters. So that's an example of how the tool works. And now Daniel is going to take over here to show a little bit what's happening behind the scenes.
Yeah, so the way we are going to to go through this is first Alejandro is going to be showing what is the interaction with the application, and then we will come back here and try to explain what's going on with diagrams. So the first thing to notice here is that we have the front end, which is the actual application that the user is going to be interacting with. Then we have on the other end, we have the Rhino server, which is running the Grasshopper script that Alejandro showed before, or any other Grasshopper script. And we have an intermediate server that is going to be simplifying how those 2 different ends talk with each other. So if you want to go ahead, Alejandro, and show what happens when the user uploads a model. We already saw more or less in the video, but we will see in the demo, so we can stop and see what happens.
So you click on the plus to upload a model. This here is going to be uploaded automatically.
So yeah, so you would see the prompt to select the model, but because this is a demo, we just upload a demo file. And the first thing that you can see here already is on the left-hand side, we have a panel that says layers, where we already split the model in layers, and you can click there to show the layers. So actually, you can already see the results that come from the backend, but we will cover that later. There's also a panel on the top right that says object summary, where you can see all the layers that we identified. And we also try to guess the layer type based on the name. So for example, if a layer has windows, we already classify or try to classify it as openings, but maybe we make a mistake on the guess, or maybe, for example, the others, we don't know what others layer has inside. So we don't set any type. The user can select that. And as soon as they select, it will be sent to Rhino. So if we go back to the diagram, we can see what's happening. Yeah, so first thing that happens is that the model is uploaded, then we identify the layers, and that flask there means that we try to guess what the layer contains based on the name. The exclamation mark is what I mentioned, that maybe we miss the type of layer and you want to edit it. And once we have the layer and the type, we send that to the intermediate server. If you show the next part, yeah. So each layer is sent separately to the backend, because that way we can process them in parallel, and we don't need to wait for one layer to finish to continue processing the next layer. And also, if we missed or if you want to change the type of layer for one single layer, we don't have to reprocess the whole model. We just process that single layer, and that's it. Then what happened next is in Rhino already, we get for each layer. So that happens for each of the layers. We identify all the objects present in the layer, and we try to translate each of those objects to the type of object we are looking for based on the type. So for example, if you have windows, we try to translate the objects that you put in your model to windows. Maybe you put a dot, and we don't know how a dot translates to a window. So that would be the red object that I put there. And what the Grasshopper returns is a layer only with the objects that we could translate. So basically, it's like filtering the things we couldn't understand. And if you go back to the demo, Alejandro, that's what we can see on the panel, the object summary panel on the top right. We show how many objects we identified, and if we have less objects identified by Grasshopper. So how many objects we found in your initial model, and how many objects we found in the translated objects. So
we can show, like, in this example, for example, these rooms were given as like a closed volume. Those other rooms were given as just like a surface for the floor. Since like the definition, the way we're defining rooms is just a surface for the floor. Like those ones are translated into just one surface on the floor. These ones are just kept as they are. And then you have this line here. That's what you were going to talk about, right? You can continue.
Yeah, so in this case, Grasshopper couldn't translate that line to a room. So because of that, you can see it's quite small, but you can see on the right-hand side, you can see the valid objects. I mean, on the properties panel, you can see it, valid objects 16 out of 17. And then we also show you in red what you uploaded, and in green what we identified in Rhino. So you can visually easily find what's going on, and what's the object we couldn't translate. So you can go and visually inspect the model and understand what's going on. What happens here, so why we do this is to give the user quick information about what they are going to estimate. Because imagine that you have a room with 3 windows, but for some reason, we couldn't identify three windows, but we identified 1. If you run the estimation there, you are just running a wrong estimation, and the results will have nothing to do with the actual estimation. So we give you the information. Maybe you want to go back to your model, see what's going on. Maybe there is a broken an object or a line that is not closed, whatever. You fix it, upload the new model fixed, and when everything is as you expect, then you can run the estimation. So if we go back to the diagram. All right. So what happens here is we get that layer with only the translated object to the intermediate server, which does nothing in this case. We just send that to the website, and you can see on the website you have this possible exclamation mark, which means we didn't identify, or we couldn't translate all the objects in that layer. And that's pretty much that first step. Then if you run an estimation, we can go to the demo and see what happens. And then we can go there. Maybe if you deselect the layer, it's probably yeah. So it basically sends the information that we need to the backend. It takes some time, and we get back the result and show them based on some like we have some color coding, very similar to, I mean, I think you already explained that in the video, Alejandro. So yeah.
Like in this case, for example, it has split this room into, it has 2 different sizes, 2 different depths, and so it has to make that section. And we can go back to that.
Yeah. So if we go back to the demo. Yeah. So what happens here is that we get all those layers that are already green because only contain the objects that we couldn't translate, and the user is happy with those objects. We put them together in a dictionary, in an object that we send. So it's not a file. It's like well, I don't know how to explain that in Rhino terms, but basically it's an object that we can send to the backend, but the object contains each different layer. It's not like a 3D file or anything. it goes to the intermediate server, and then it is the intermediate server, the one responsible to build that 3DM file. So we actually based like starting from the layers we got from the user, we build a 3DM file, like the whole file with the properties and everything, and we send that file to Rhino to the Rhino server. Rhino runs the algorithms and processes that it needs to run, and the result is another file with the results, like the rooms with different colors, and 2 pieces of text, which are the recommendations for failing rooms, like the rooms that didn't comply with the regulations, both in English and in Swedish. And we get those 3 things. They are sent to the intermediate server. In the intermediate server, we attach as attributes to the actual. So inside, this is already inside the 3D file. We get the text in English and Swedish, and we attach for each object the corresponding text. That way, it's much easier on the front end to, when you click on the room, to show that specific text, like the recommendation text. That file, that 3D file with the text already attached as attributes to each object, is sent to the front end, and then in the front end, like the application, we already show you results with the color scales and everything on top of your model, so you can see which are which ones are the rooms that don't meet the criteria and so on. So that's pretty much what is going on. So
now we just mention this here we're just going to summarize the key learnings.
Alejandro,
yeah,
we cannot hear you.
yeah, it's quite
super complicated. Yeah.
But now, okay, so now we're going to talk about the key learnings.
It's not very good.
No.
Let me just
quite difficult to understand what you are saying right now.
Is it better now?
Not really.
No.
Now. Okay.
No.
But do you want to take the slide then?
Yeah, I can cover this one on the next few ones, and then.
So,
right,
are you sharing your screen, Alejandro?
I am sure.
Yep.
Daniel, could you share the same document or?
No, because I don't have PowerPoint, so I don't know.
And could you continue, Daniel?
Yeah, I can cover not all of it because the last part is Alejandro's, but I can, like, the next few slides I can cover.
Okay, thanks.
So maybe we see later if the audio has improved. So after working on this, we identify some key points that we want to raise and potential improvements to how this could be done. The first point is the improvements needed in the Rhino.Compute API docs. We will cover them one by one. So let's just go through them and then we go deeper. The second part is moving computation to the front end when possible. Then some difficulties we found working with Grasshopper. So because when Grasshopper interacts with a website, it's not the same as running the Grasshopper script on Rhino. So there are like the interaction with the website, and iterating on that was a challenge sometimes. Then potential for smart topological structures in Rhino, which Alejandro will cover later. The importance of including a UX designer, and the potential of data science for performance analysis. So if we go into the first one, so the first thing is we know the Rhino.Compute was in beta, and during this process we could reach out both in the forums via email or actually any method to contact McNeel developers, especially Luis Fraguada was very helpful. But there are like the fact that we needed to reach out to McNeel developers means that there is something missing in the documentation, which we understand because it was in beta. But some of the things that could be improved is, for example, the fact that there are multiple libraries. For example, the image you see on the right are the libraries that you can use for interacting with Rhino. And for example, there are 3 for Python, 2 for JavaScript. It was a bit confusing sometimes knowing which library you needed to use, what docs you need to read. So yeah, that's something that could be improved. And so like the next point is making the API more language friendly, which maybe doesn't mean a lot, but I will try to show with the next slide. So if
there was also that documentation was sometimes incomplete.
Oh, the audio is really bad now. I couldn't understand anything.
Okay, never mind.
So maybe it's the connection, and now it's actually a bit better. I don't know if something changed.
Yeah, some of the documentation was incomplete.
Oh yeah, so like for example the 3DM.js, the Rhino 3DM.js it's like a wrapper on top of I think a C library or something, or a WebAssembly library, and sometimes the docs are just empty. So they make references to other docs in other languages, and sometimes the arguments to the functions are different, or maybe the function is not there because the bridge didn't implement it. So yeah, it was a bit challenging sometimes getting things to work. So yeah, going back to the making the API more language friendly. On the left side, you can see how you send information to Rhino, or at least how you build the data structure holding information that you will send to Rhino. And you have to create a tree, then you have to put you have to create one data tree for each of the properties you want to send, and then you have to append all that to the tree, and you send that to Rhino. But in JavaScript, the most usual way to do something like that is building a JavaScript object where you just put some properties and some values. So maybe a small wrapper on top of the data tree and all that could simplify things a lot when building this object to communicate with Grasshopper. And then when you receive information, which is the next slide, can you go to the this one? No, the previous one. Yeah, I think there is a delay on the slides. Well, so this is what you have to do when you get that result from Rhino. On the left-hand side, you see, like, if you understand a bit of JavaScript, it's like you have to define some variables, then iterate over some objects, compare different strings, and then if the string matches, then you just go to a property named curly braces, 0 curly braces, which is not very common. So, I mean, I guess this comes from the SDK being compatible with multiple languages, and maybe this is normal in other languages. But again, in JavaScript, I would expect to be able to do something like what you can see on the right-hand side, where you get the result, and the result has a property named values, and then you just access each of the values by the name without having to iterate or do things like that. So yeah, that's what I meant by making the API a bit more language friendly. The next slide is about moving things to the front end. So for example, in our project, the first step where you get the model and split the model into different layers, that was done initially with a Grasshopper script. What happens is you need to send that to Grasshopper, wait for the response, and then process the response. So that takes time, and that takes computing Rhino.Compute computing. So there are opportunities like this sometimes. Like if you inspect what you're doing and what the scripts that you have in Rhino are doing, maybe you identify some opportunities to move things to the front end. And the results, if you do that, is that it's going to be faster because you don't need to send a response, do some processing on a computer somewhere else, and then getting a response. You just do that on the client's computer, like the user computer, and that is going to give you a feel of real time. So you upload the model and you instantly see all the layers. You didn't see a spinner like we are processing your layers or stuff like that. So the experience for the end user is much better if you do that. And then there's also the advantage that if you do it, Rhino.Compute won't have the same amount of load. So you will decrease Rhino.Compute load. And that is probably going to make processing, like it's going to make your application cheaper because maybe you don't need to scale your servers to 2-3 instances. Maybe with one instance, it's already enough. So those are things to keep in mind when interacting with Rhino.Compute from a front end. Maybe there is an opportunity to move things to the front end. The next one. So this is what I mentioned before about having challenges sometimes testing the Grasshopper script. So many times what happened is that Alejandro would make an iteration on the Grasshopper script, and he would send me the file, the Grasshopper file, and then he would have to wait until I was online and had the time to get into the file and interact with the file through the application, like sending an actual geometry or sending some, like for example, the layers and the types, like sending the actual things to the Grasshopper script and waiting for a response. What happens is that sometimes the information that is sent couldn't be processed by the Grasshopper script, or the results didn't match what I was expecting on the front end, or there was an error. Maybe some block failed and there wasn't any response at all. So the problem here was that Alejandro couldn't iterate on Grasshopper scripts on his own. So he had to wait for me, for a developer to run this and then give him feedback. And based on that, he would iterate. To solve this problem, we created a Grasshopper inspector, which is a small application where you upload a Grasshopper script. Yeah, we are going to show the Grasshopper script. Let's see. There. Okay, so there on the top, you select the Grasshopper script, and then you can set some script inputs. There are different types, so based on whatever you need to receive into your Grasshopper script, you can set the type.
Danny, let me try to do this. Let's see if I disconnect.
Let's see.
Can you hear me better now?
Yeah.
Yeah.
Yeah. Let me see, maybe because we don't have more videos or anything, no? Maybe if you send me the slides, maybe I can try to open the slides.
Can you hear me?
Yeah.
Yes.
And maybe it's fixed.
Okay. Now, sorry. Can you hear me now?
Yeah.
Yeah.
Okay. Great. I think the problem was the extra screen that I connected to my computer that was missing. So.
Okay.
So
but
I'm sharing
now
my screen.
you are not sharing now, I think. I don't see it.
No.
Now. Okay. Cool.
Okay. So let me do this demo myself of this this script inspector. So here I have a very simple Grasshopper script that is just creating. You have a box here. It's scaling that box by a certain factor that you give it, right? and then it's just moving that box to the origin of coordinates. So it's a very simple script, and now we want to check if this script works on Rhino.Compute. So for that, we need inputs and outputs. So we're just gonna connect our input can be the scale factor, and for that we're gonna connect this get number, and we're gonna call it scale factor. And then we need the output. We can have this context bake. So we can have as output the box scaled, and then the box scaled and moved. So we can call this box scaled and and box scaled and moved. So we save this, and then we load it into this Grasshopper inspector. Then we can decide. We need to define the inputs. So in this case, we have an input that is a number that we call scale factor, and then we can give it a value. Like in this case, I give it 10, and then we run it, and you see, like here, we get all the outputs. We're not getting any outputs. Oh wait, I have uploaded the wrong file. It's this one. Yeah, let's try it now. Now we're getting some input. So we're getting two outputs basically. The box, see, like you have this output is a B-rep, it's what it's supposed to be, and the other one is another B-rep. So the box scale and the box scale and move. So if we would, for example, if there was some problem in the script here between this output and this output, and we save this again, and I upload it again. And I run it. Now we should be getting, we should not be getting anything in the last one. This is taking a bit too long. Well, okay, it got hanged somehow, but that's what it would happen. Like you would not be getting any results in the second one. So this is very useful, like when you have very big scripts like this one, because this is the script that we were trying well, when we were working, and we were having we had some input here, and then all the outputs here. So something was going wrong, and we were not able to know. We were completely in the dark because we could not reproduce the same problem in Grasshopper. So then what we did was we started putting intermediate outputs, so we know where the data flow was reaching and where we have to focus to solve the problem. And I can take this from here, from this slide. The next key learning is that we needed to make our own topological structure within Rhino ad hoc. And this topological structure is the one that was used to connect the different geometrical elements. For example, assigning balconies to windows, or windows to rooms, rooms to floors, floors to buildings, etc. And this was very important, not only for the obvious reasons of making this hierarchy and assign and being able to apply the equation, but also to be able to split the rooms. For example, identify rooms that were corner rooms that we had to apply the equation in a different way, or split the rooms that were irregular, that had some parts that were a deeper part and a less deep part, and so on. So we had to create a very complex system with to take in consideration all these cases. And but we created this topological system, but it was based on spatial closeness between the different elements. So it was not a smart system. It was like a relatively dumb system. So we would have loved, and this is like a suggestion, like for McNeel, that this if Rhino could have a built-in topological system, we see a lot of potential for for many things, but especially for like performance analysis, because most performance analysis you need to have some kind of like topological system to relate all the geometries. So we would that would have been made our life much easier developing stuff like this. So it would have made Rhino an even more powerful tool than it is nowadays. Then the importance of including an UX designer, like this is I think Danny he already was aware of the importance of a UX designer. I was maybe not that aware of it. So this is here in the screen. You see like what our interface looked like before we got some input from Laura. That is what is our UX designer. And then after just like a few hours that Laura took to like make some improvements, we have the interface that you saw that we presented that is significantly more intuitive, more clear, more visually appealing, and so on. So this was a very well invested time, I think. And the last one is that we have the last key learning that we drew from this project is that we have confirmed our hypothesis that data science brings a huge potential also to integrating performance analysis in architecture. And it does this by simplifying them, but also by improving how it can be integrated into the workflow of architects and other non-specialists, people who don't necessarily are experts. And it reduces like all these like iteration need for cumbersome iterations and like exchanging information between different software and so on. That was it from us. Thank you for listening, and we look forward to hearing your comments or questions.
Okay, thank you very much, guys, for your presentation. And sorry for the problems in the Alejandro's audio to the audience. Yeah, there are some questions, some interesting ones. So I want to ask about the file upload. Omkar has a question. Where is the Grasshopper script hosted? And about this also, Justina has a good question, which is if you need to have an upload Rhino model or a Grasshopper file, what's the benefit of using this web tool in front of running the Grasshopper locally?
Do you want me to cover the first one, Alejandro?
Absolutely.
So the Grasshopper file is actually sent to Rhino in every request. So when you saw in the diagrams, when we go from the intermediate server to Rhino, the intermediate server has the Grasshopper file, and it has to transform that to base64, or I don't remember exactly what is the encoding of the file, but basically you have to encode the file and send that in the request. So actually, I think if you go back to the to improvements on the API, I think we can see there. Yeah, so the second one with the text. The next one, that one. So when you call the API to interact with Rhino from Node.js in this case, you can see Rhino.Compute.Grasshopper.evaluate definition. And that definition, the first argument on that function call, is the encoded Grasshopper file. I remember we were talking with Andy from McNeel, and there's a way to somehow cache to cache the definition on Rhino.Compute. But we learned about this after the solution was implemented, and we didn't put the time to, we didn't invest the time to make the changes. But I know there are more options, but this is the way we did it. And if you want to go with the second one.
Which second one? This one. The second.
The second question.
The second question. Yeah.
Yes, the second question was about why do we need to do this on Rhino.Compute, right?
Yeah.
Yeah, so there's two reasons. Well, first one is like in this case we were uploading a Rhino model, but this potentially can also upload other types of models. So you're reaching other architects that are not necessarily working with Rhino. So you could upload an AutoCAD file or a Revit file or stuff like that. So that's one reason. The second reason is that the idea was that this would be used internally by architects at White, but in a first stage, but in a later stage, we wanted to be able to sell this as an external service to other architectural firms. And that then basically, if you just have like a Grasshopper script that does this, then basically you just have to send them your Grasshopper file, and then you can't really, once you give them your Grasshopper file, you have given them everything, right? You can't continue charging. So we instead of selling this as a product, so just the product being like a Grasshopper file that they would buy from us, we want to sell this as a service. And to sell this as a service, we had to have it on a website that we could have everything was happening on our site, right? So we were not sharing any Grasshopper files or anything. They were uploading a Rhino model, and then they were getting some results, but everything else in between was happening in our site. We have full control of everything else. We don't need to share it. That's basically the reason why we chose Rhino to do this.
Okay. So Justina has another question. Does Grasshopper Script Inspector print the response from compute server, or it's running some additional checks on top?
No, it's just,
So,
yeah.
You can ask. So basically, it just receives whatever the Rhino.Compute response, so the actual object that we receive from the Grasshopper script, and we just show that. So there's nothing done on top. Maybe she's asking because of the errors and values. So actually, if there is an error, the answer that we get from the server has that property called errors. So we don't check for errors. If there are errors in the Grasshopper script, they come already within the response. So we just show the response we get from the server.
Do you guys know hops?
So I think hops,
the plugin, hops can be used as a local debugger for compute as well.
Yeah, so actually, I think hops is the tool that I mentioned before that would cache the Grasshopper script, and that was a different approach. And Andy told us about hops, but we were already too far in the implementation of the solution, and we didn't invest the time in using hops. But yeah, hops is definitely something to check out if people are trying to do something like this.
Yeah, hops runs a local server. So actually, if your Grasshopper script works on using hops, you can be completely sure that it will also work in a web application or in another interface calling to compute. So more questions. For someone who is an architect having no clue of JavaScript, how would I access this with clarity, starting with a Rhino model? This is a question from Nisha. Okay, so she's, I think, an architect with no knowledge of JavaScript. So how can she access this with clarity?
Access, I'm guessing. I mean, because she doesn't need to know any JavaScript to use this tool. Like, I'm guessing, like, how could she do something similar to this, no? Without any Java knowledge. I guess that's what she's asking.
Yeah, probably, yeah.
I guess the short answer is that you need to have some knowledge, right?
Yeah.
Or someone that helps you, like Daniel. Like, you need to have someone with front experience.
Okay. Okay, next one. Ali Nasiri, can you please elaborate more on Node, the intermediate server, and why you need it?
Yeah, so that's actually a very good question, because ideally we shouldn't need the server, but and this is something we didn't touch on the presentation because like we were getting some problems trying to do that on the front end. With that, when I say trying to do that, I mean everything that we did on the intermediate server ideally should be done or should be able to be done in the front end, but we were having issues. I think I know more or less where the issues could come from, but because we had the server available for other stuff that we were doing, like for example, the first implementation with just the room, we like a fast solution for us was using Node, which was working nicely. I think the reason why we couldn't get this working on the front end is because to use Rhino.Compute, you need a WebAssembly file that you have to specify when you load or when you interact with Rhino. With Rhino.Compute or with Rhino 3DM. This is part of the confusing things about the multiple SDKs. But basically, whenever you want to do something like creating a 3DM file or stuff like that, you would have to use that library where you have to set a WebAssembly file. That WebAssembly file is like the C implementation of the library, transformed in a way that the browser can understand. The problem is the 3JS library we were using, the one that shows the 3D models and so on, also has also needs a WebAssembly file for translating Rhino 3DM models into those 3D views. And my guess is that there was some incompatibility there. We didn't go much farther than just this doesn't work very well. Spent a few hours trying to solve it, and then decided to go back to using Node because it was working. And yeah, that's a good question. It should be possible. We didn't manage to do it, and Node was a viable alternative that we ended up using. That's it.
Well, Henning wants to point that Luis template in the app server in our McNeel repo has an auto UI that creates a UI from the Grasshopper file. And that's why when you send a Grasshopper definition to compute, you can check in the response what inputs it has, and it creates automatically the controls in JavaScript. Let me see the next question. So Elsa Minshut wants to know, when opening a Rhino file, how precise is the tool in identifying the geometry as different elements of the building? How does it determine, for example, that a window is a window if there is no topological relations between the elements?
So it's just based on the name of the layer. So it tries to look for English and Swedish words, key English and Swedish words, and if it finds like the word window or the word fönster in Swedish, it puts it automatically as a window layer, and then it tries to read everything that is in that layer and tries to read it as windows. But if for some reason the name is wrong or it has a name that somehow misleads the system into thinking that it's something else, then you can just go through the list of layers and change it and say, okay, this layer was identified as windows, but it's actually rooms. Then it changes it. Then it tries to.
I think the question was more about the translating the objects into windows, for example, rather than guessing the type of layer. No, like how do you know a circle is a window, or how do you know a box is a room or a surface is a room? No?
Exactly.
Okay, if that's the question, then it's like, for example, if rooms are defined as horizontal surfaces. So if you give it a vertical surface, it's gonna ignore that element because it's like, I don't know what to do with this. But if you give it a box, it's just gonna take the lower part of the box to say, okay, this is some rooms can be modeled as a box or as a closed volume. Then I'm just gonna take the lower surface and I'm gonna take this as my room. If you give it like a closed or a horizontal polyline, it's gonna say, okay, this is a closed horizontal polyline. I know how to translate this into a surface. Then I'm gonna do that, and then this is gonna be my room. So it's trying to take in consideration all the possible ways the user would have modeled this room, and then convert them into the type of geometry that we're taking into our grasshopper model. And whatever that doesn't, that the script doesn't know how to transform into the right type of geometry, it ignores, and it gives you this disclaimer, this warning that we didn't know there's 2 objects or whatever number of objects that we didn't know how to interpret.
Okay. And Christina wants some tips for someone starting with Rhino.Compute and well, integrated with a website. Do you have any tips for Christina?
Yeah, I mean, just if you have any idea, just start testing, and I mean, in our experience, like someone else asked before, you're probably gonna have someone that knows a little bit about front end if you don't know yourself. So you're gonna have to do this as a collaboration.
Good one. Okay. Any questions? Eleni wants to know if this tool can predict daylight performance in a room with roof windows.
No, that's a limitation. Like the equation that we did was limited to horizontal to vertical windows. So no skylights.
Okay, there are no more questions from the audience. So I think this is the end of the session. So, well, Alejandro, Daniel, thank you very much for your time, for your presentation, for your effort. And
thank you for having us.
Thanks for giving us the opportunity.
Yeah, super interesting talk today. Thanks to the audience also for being here and for questions. And I hope see you in the next videos. So have a nice day.
Bye.
Bye.
Bye.